All right, in this example, we're looking at the first rule or the first type of partial fraction. So you can see this is a proper fraction, right? We've got an x over an x squared. So we can't use algebraic fractions to split it up into, algebraic long division to split it up into something a little bit simpler. What we need to do is to use this idea of partial fractions. So there's three different types of partial fractions, three different types of decomposing a proper fraction into partial fractions that we're going to get. And this first one is the unique linear factors. So basically what it's saying is that if we have something where the denominator has unique linear factors, so the first linear factor is x, the other one is x plus 1. Whereas something like this, it doesn't, right? We've got x plus 1 squared. That means there's two x plus 1s. They're not unique. What we do is we know that we can split this partial fraction up into something over x plus something else over x plus 1. So really what we're doing is kind of like reversing the fraction idea. If you think, well, back in like year 10, you would have gotten that fraction and then gotten the same denominator, added them together to get this. We're doing the reverse. We're splitting it back up so it's easier to integrate. So what we're going to do is go ahead and find out, well, what were the two fractions initially? And then go from there. So what we do is we split it up into those two parts of the denominator. We've got a over x plus b over x plus 1. So we split it up because you can think, all right, well, that would be a outside of x plus 1 over x plus 1. And that would be bx over x plus 1. Right, and we know that we can add these two fractions together now, and the two numerators would add together to give us 2x plus 5. So we're reversing the adding fractions together idea, essentially. Okay? And that's the idea of partial fractions. We're splitting them back up into something more simpler that in year 10 you would have gotten, you would have gotten this as a question with values for a and b, obviously. You would have gotten this for a question, had to get that common denominator, and then add together the numerators to get our fraction that we've got. So we're splitting it back up. So from there, we know that the denominator is going to work, and pretty much we can say, well, the numerator of 2x plus 5 has to be equal to a outside of x plus 1 plus bx, right? Because we know that these two numerators will add together to give this numerator. Then from there, I can say, well, 2x plus 5 has to equal ax plus a plus bx. All right. So we can tell straight away, right, that the ax and the bx have to add together to give 2x, and the constant a has to equal 5. So we can say, well, a is equal to 5. And we can also say, well, 2x is going to be equal to ax plus bx. All right, so if a is 5, then that means b has to be equal to -3. All right, from there, we're going to say, well, 2x plus 5 over x plus 1 with x out the front, dx is equal to the integral of 5 over x, take the integral of 3 over x plus 1. And they're both with respect to x. Okay, so that's what we've got going on. So now integrating this becomes a lot simpler, right? 5 on x just integrates to 5 outside of ln x, and this just integrates to 3 outside of ln x plus 1. All right, so the idea of partial fractions is taking something that's quite complicated and we can't use substitution for, to split it up into two fractions that are actually quite simple. So that's the idea of partial fractions. I think you could go down the road of expanding those brackets and then trying to work it through with ln from there, but we'll get to a point where we might not necessarily be able to do that. Okay, but that is the end of this example.